This is the solution to random MathStat problem number 184, where we're given x1 and x2, IID, or a random sample of size 2 from the standard normal distribution, and we're asked to find the distribution of the ratio x1 over x2. There are many ways you can approach this problem, but the MathStat approach, based on what we know so far, is for us to use the Jacobian method. The Jacobian method allows us to transform from a joint PDF for two random variables to a joint PDF for another two random variables, y1 and y2, where each of y1 and y2 are functions of the original x1 and x2. In this case, we don't have any y's in the problem, but we do care about the distribution of x1 divided by x2. So I'm going to define y1 to be this ratio, and then I'm going to define y2 to be another function of x1 and x2 that's going to be convenient to work with. We'll then find the joint PDF for y1 and y2 and ultimately integrate out y2 to get the PDF for y1 alone. As a reminder, the PDF for the standard normal distribution is 1 over the square root of 2 pi times e to the negative 1/2 x squared. The joint PDF for x1 and x2, denoted by an f sub x1, x2, is, by independence, the product of the two marginal PDFs. You'll notice that I don't have a subscript on the f. In other words, there's no f1 and f2 because x1 and x2 are identically distributed and both come from the same distribution with the same PDF, which is given right here. Plugging in x1 and x2 here and multiplying these PDFs together, we get 1 over 2 pi times e to the negative 1/2 times the quantity x1 squared plus x2 squared. Consider now letting y1 be a function g1 of x1 and x2 and defining that function to be the ratio x1 divided by x2. We've noted in this course that when choosing a second function of x1 and x2 and working with a ratio, it's easiest to let your second function be the denominator. So I'm going to let y2 be a function g2 of x1 and x2 and define that to be just this denominator, x2. We want to invert this system of equations. I could still be using capital letters and random variables, but this is just an algebra step, so it doesn't matter. I want to solve for x1 and x2, and that's easy enough here. This is going to be the function we called g1 inverse of y1, y2, and this is going to be the function we called g2 inverse of y1 and y2. But recall that that notation is maybe not the best because g1 inverse is not the inverse of the function g1 alone, and the same is true for g2 inverse. Rather, we have to invert the system simultaneously. Our g1 inverse of y1 and y2 is defined by our solution for x1, and our g2 inverse of y1 and y2 is defined by our solution for x2. We now need to compute the Jacobian for the transformation. Recall that this is the determinant of a matrix of partial derivatives like this. For the first row, I'm going to consider my expression for x1 in terms of the y's, and I'm going to take the derivative first with respect to y1 and then with respect to y2. The top row of this Jacobian will become y2, y1. For the bottom row, I'm going to consider my expression for x2. Taking the derivative of this with respect to y1 is 0, and with respect to y2 is 1. So we end up with wanting to find the determinant of this matrix, which is simply y2. The joint PDF for y1 and y2 is given by this analog to our G inverse formula in the one-dimensional case. I'm going to plug in G1 inverse and G2 inverse, which are y1 times y2 and y2 respectively, to the joint PDF for x, and I'm not going to forget to multiply by the Jacobian on the end. To finish this problem, we need to integrate out y2, so I'm going to write this. I'm going to clean this up just a little bit. I'm going to put this absolute value of y2 in the front, and I'm going to factor y2 out of this exponent to try to isolate it as much as I can. The marginal PDF for y1 alone, which is what we ultimately want, is going to be the integral of this joint PDF over all values of y2 from minus infinity to infinity. Here I've written this integral with a constant c, where c is 1 plus y1 squared, because it's a little cleaner to go forward in the solution of this problem. At the moment, you can think of this argument y1 as constant as you run over all values of y2. How do we deal with an integral involving an absolute value? The usual approach is to rewrite the integral as a sum of two integrals. In one of them, you'll integrate over all values for which the argument of the absolute value is positive, and the other integral, you'll integrate over all values for which the argument of the absolute value is negative, and then for each integral, you will write the integrand without the absolute value accordingly. Note, however, that for this integral, the integrand is symmetric in y2. That is, if I plug in y2 equals 3.7, I'll get the same thing that I get if I plug in y2 equals negative 3.7. Therefore, I can rewrite this integral as 2 times the integral going only from 0 to infinity over y2. In this case, I'm running over only positive values for y2, so I can drop the absolute value. To do this integral, it is a straightforward u substitution problem where you can take u to be c times y2 squared or something similar, basically this exponent. So you can include the 1/2 or you can include the negative and the 1/2 in your definition of u, but you'll notice your du is essentially out here. Method 2 for computing this is our new integrating without integrating approach. Here, I'll focus in on the variable part of the integrand, ignoring constants. Do you recognize this PDF? If you go to the continuous side of your table of distributions, you can begin to narrow down the search by first considering all distributions whose support is 0 to infinity. To further narrow down your search, you can then go into those PDFs and look for the ones that have an E. This leaves you with probably an exponential distribution, a normal distribution, a gamma distribution, and something known as a Weibull distribution. Upon further inspection, this is closest to the Weibull distribution, which has a PDF that looks like this. This PDF has 3 parameters, an alpha, a beta, and a gamma. Those are not standard parameter names. There really isn't a standard. And a lot of people will ignore the alpha altogether, which is just sort of a way of recentering this distribution. But this is the Weibull PDF in our table for this course. Imagining x as y2, we want to sort of match this and this, ignoring constants out front, to try to figure out the values of alpha, beta, and gamma. Because of this indicator and the fact that we don't see differences like this up here, it's easy to see that alpha is 0. Looking in on the exponent on the e, it's easy to see that gamma is 2. The beta is a little harder to find. I'm going to focus on this exponent. If I take negative 1/2 c times y2 squared and aim to write it in this form, I'm going to bring the c and the 1/2 inside the square by putting a square root on them. I am going to flip that ratio and put it in the denominator and put in a -0 in place of the minus alpha. You can see again here, matching this with this, that alpha is 0 and gamma is 2, and now it becomes clear that beta is the square root of 2 over c. If you did everything right up to this point, you don't need to worry about going back and dealing with and matching any of these leading constants out here. With our now defined parameters for alpha, beta, and gamma, the Weibull PDF simplifies to this. Recall that we're trying to find the marginal PDF for y1 by doing this integral. I want to make this integrand look like this. So I'm going to leave some space here And then I'm going to plug in a c here and compensate by putting a 1 over c out here. Now I'm integrating from 0 to infinity the Weibull PDF on 0 to infinity, and this integral is simply 1. In conclusion, the marginal PDF for y1 is 1 over pi times c, and plugging c back in, we get an expression like this, and y1 is allowed to range from minus infinity to infinity. Y1 is the ratio x1 over x2, so we have found its PDF, and we want to name this distribution. If you go to your table of distributions on the continuous side, you can narrow this down by looking at all distributions that have support from minus infinity to infinity. And then maybe you can look for distributions involving pi. There is one issue with that approach, though, and that is, even though we haven't talked about it, the gamma function of 1/2 actually evaluates to the square root of pi. So for the right parameters, our gamma distribution could get a pi in it. But our gamma distribution only lives on the support set from 0 to infinity. After some searching through the table, we realize that this is the PDF for the Cauchy distribution. The Cauchy PDF is given in the table like this. Other people might use different parameters. But matching this PDF with this PDF up here and trying to figure out what alpha and beta are, we see that our ratio x1 over x2, which we called y1, has a Cauchy distribution with alpha equals 0 and beta equals 1. Be careful when referencing other sources. This notation is not standard, like we have standard notation for a normal distribution or kind of standard notation for the exponential distribution. So when I write this, I mean something with this PDF.